Hi there. My name is David Tudor. I'm a mathematician, and I've done mathematical modeling of spread of infectious diseases now for about 45 years. So I was particularly interested when I saw on YouTube Senator John Kennedy grilling Chad Wolf, the acting Homeland Security Director, about how little he knew about mathematical modeling. And it seemed that Senator Kennedy expected Mr. Wolf to know all of these things already. It seems to be, in this video, I want to show you some of the mathematical modeling that is done in this kind of a disease outbreak. And just in case someday you might become a director of Homeland Security and be grilled by someone about spread of infectious diseases, in case you're interested in the philosophical background for mathematical modeling, there's a link here you can copy or download this file that I'm showing you now. This file, including with all the programs that I've used to show you this modeling exercise, you can download. I will show you a link where you can download at the end of the video. So we'll start with some basic definitions. I'm going to do this fairly rapidly. This is mathematics. Most people don't love mathematics, so I will try to minimize, but we can't do mathematical modeling without looking at the mathematics part. At any rate, the basic definitions that we use: a susceptible person is someone who does not have the disease, is able to catch the disease, and is active in the population, that is moving around, coming in contact with other people as you do in your normal lives. An infective is someone who has the disease and is actively moving about in the population and likely to spread the disease. And a removed person in this kind of disease is one who's had the disease, recovered, and is immune afterwards. We'll see some other types of diseases in a second, but the coronavirus seems to be one that you recover from and become immune. We'll talk about rates here. Rates are number of events per unit time. The contact rate example, we'll use the Greek letter lambda for that, is the number of contacts of a typical infective per unit time that are adequate to transmit the disease if the other person contacted is susceptible. So with that in mind, those three categories of diseases, let's go down and look at different types of diseases. An SI disease is one where the person is susceptible, becomes infected, and then remains infective for the rest of their lives. So herpes is an example of that. An SIS disease is one where you become infective, recover, but you can catch the disease again. If I group all of the common cold viruses together, then the common cold would be something that would be an SIS disease. An SIR disease is one where the person who is susceptible becomes infective, can spread the disease, but then recovers and stays immune. So we're presuming that here the coronavirus is, as far as we know, an SIR disease. So we will do the SIR modeling approach here. Now, an SIRS disease, there have been some rumors that the coronavirus you might lose immunity and become infective or susceptible again. After catching the disease, you would be immune for some period of time, but then lose that immunity and become susceptible again. There are all kinds of variations on these types of diseases. SIRI, SIRIS, you can explore the literature if you're really interested in becoming a disease modeler. The rates that we're going to use here are lambda, as I mentioned before, the number of contacts per unit time that a typical infective person will make, contacts that will transmit the disease if the person contacted is susceptible. So note here that contacts with removed persons are still contacts, but the disease is not transmitted. Beta we'll use as the birth rate. Delta is the death rate, not due to disease, or not among infective people. So we will presume that the death rate is the same for people who are susceptible as it is for people who are removed, so that having had the disease does not increase your probability of death. The delta D is going to be the death rate of infected persons, and we'll assume that that could be elevated with respect to the non-infected population. This idea of differential death rates actually makes the number of individuals in the population a variable rather than a constant term. So the last rate that we'll use is the rho, is the recovery rate from the disease per unit time. So all of these rates are per unit time. Now let's go back and look or not go back, but now let's go forward and look at the model. The functions that we're going to use in the model: S of t is the fraction of the population that's susceptible, I is the fraction that's infective, R is the fraction of the population that's removed, and N of t is the number of people in the population at time t. And we will use time here and measured in weeks. And as I said a second ago, N does become a function of time if we allow disease-related deaths. Now, N is the number of people in the population, and S is the fraction who are susceptible. So NS is the number of people in the population who are susceptible. The same for I and R, and the primes there refer to the rate of change with respect to time. So these equations describe how the numbers of individuals change with respect to time. Lambda is the contact rate, so these people, there are lambda people contacted per unit time by each one infective, but there are IN infectives, since I is the fraction of the population, so IN is the number of infected. So each of these infected people are going to be contacting lambda other people, but only the fraction S is susceptible. So this is the number of cases that are transmitted per unit time. And notice that these transmitted cases go down here. That's why I put a plus there. The people who are infected in the susceptible class go into the susceptible class, or to go into the infective class. This is the birth rate. We're presuming that all births are into the susceptible class, so no one is born with the coronavirus. And here's the death rate. There are S times N susceptibles, and they die at a rate of delta. Going down to the infectives now, we saw that the new infectives come into the infected population. There is a delta death, disease-related death rate. So IN is the number of infectives times delta is the number that we lose per unit time due to death. And rho is the recovery rate. So this number of individuals in the infective population will go down here. That's again why I put the plus here, into the removed population. So people, how do we get removed? They either recover from the disease or they die. So this is the death rate from the removed. So the total population is the sum of NS plus NI plus NR. So if I add these three equations together, I get the equation for the change in the population. And it's the sum of all these right-hand sides, which leaves me with just beta N there. The lambdas cancel here. The rows cancel there. So I simply have the births coming into the population, into the susceptible class, minus the deaths due to different causes. So the SNs and the RNs are going to die at the same rate, and I have infectives that die at an elevated rate due to the disease. So note that S and I and R are the fractions of the population, and everyone in the population falls into one of these three categories, so that sum of those fractions has to add up to 1. Now, you may remember, if you've had any calculus, that there's a thing called a product rule for calculating the rates of a product, is N prime S plus NS prime. So if we take that on the left-hand sides here of this equation, let me go back up here. On the left-hand side, I have NS, NI, NR, and if I use this formula for the product for each one of those equations, I replace the left-hand side by that product rule. I divide both sides of the equations by N and subtract the terms N prime over N that I have on the left. You can do these calculations maybe yourself. You get these equations here. These are the same equations we had before, but notice that I've replaced the NS, NI, NR by the S primes, I prime, R prime, and these are the leftover terms that I have to subtract from both sides because of the product rule. So this is my new equation, and in fact, notice in the equation, the rate equation for the population, I have N prime over N since I divided everything by N. So I can take this right-hand side here and replace it here on the right in the first three equations. And if I do that, if we eliminate the terms by replacing that, then this system of equations right here, this system is my new system of equations. The S prime is this minus the part from the product rule there. So now I have a system of differential equations, and for what we want to do today, this is the equation we're going to stop with, because this we can actually plug into the computer program that will solve the equations and tell us what the S, I, and R functions, how they behave. So the first task then that we have to do here on the bottom is we have to estimate the parameters, all of those Greek letters, we have to estimate them. Then we can take all these numbers with all the estimates and we can plug it into a computer program and see what happens to the disease. So we're going to leave that now, and I'm going to go over to the computer programs. First of all, let me say that we're using a language called R, which is a platform for doing statistics and mathematical things. It's a very good program. I'll give you a link that will allow you to, that will show you how to download it and install it so that you can run these programs. You'll get these programs in a download file, as well as the presentation of the theory. So here the first thing I've done is to write a function that allows us to print out the definitions of all the terms that we'll be using in the models. So you can see that S and I and R in there. And the most important though for us will be, as we play around, the lambdas, number of contacts per unit time, births and death rates, and so we can review that at any particular time we want to. Then we have a function that simply prints out the differential equation if we want to review the equations that are being solved. And I have programmed certain initial values that we'll look at more closely now. If ever you want to see, you'll be able to change them in the program yourself. So we'll explore some of the possibilities. Just to see where they came from, lambda is the contact rate for each infective. Here we're saying that there are 5 contacts per week. We can change that to 2, or we can change it to 10. You can explore and see what the effect is. The beta is the birth rate. I've taken the birth rate in the UK and reduced it down to a weekly birth rate. Our unit of time are weeks here. Then delta is the death rate for the susceptibles and removes. Delta D is 3.4% higher than the usual death rate for people who are not infected. Remember that delta D is the disease-related death rate. Rho is the recovery rate. I've taken 10 weeks here. We'll be able to play with rho. Lambda and rho, I think, will be the 2 parameters that we'll play with mostly in order to see, not just play, but to see what the impacts are and see where we can have the most effect on trying to combat the disease. The program that I'm using here to solve the equation is called DESolve. It's a package in R. And I'm going to look at times going up to 20 weeks and see what the evolution of the disease is. So this is the function that actually calls, you can see it calls here ODE, ordinary differential equation, and plots out the behavior of the function. So let's go down to R. Here we are. And remember that the functions that we have available to us, let me put this over here. We looked at the definitions, we looked at the differential equations, and we looked at default initiatives. So if we say here, click into R and say print definitions, you always have to put the parentheses here. Those are our definitions. SIR and N is the number of individuals. Lambda, the number of contacts per unit time for an infective individual. The birth rate, the normal death rate, the disease-related death rate, and the recovery rate. So those are the parameters. Also, we said that we could print the differential equation if we wanted to and remind ourselves what it is. There are the differential equations that we are talking about. Most of you won't be interested in printing that again. Here, the default initial values, default inits, that tells us what the numbers are that we, by default, are going to be put into the program. So let's go back and look at the program here. Remember that the program, the name of the program is analyze, and we have lambda, beta, delta, delta D, and rho, and I, the initial fraction of susceptibles that we put into there. So there are 5 categories, 5 variables we have to put in there. Just a second. Let's go down here to R. We have to always click into R. Analyze. If I put just the parentheses in there without changing any of the values, my program will run, solve the equation for 20 weeks with these default initial values. So if I do that, I see that with these default initial values, I have an outbreak. I have here, if I look at my infectives, I have nobody infected for a couple of weeks, and then suddenly there's a tremendous increase up to more than 80% of the population infective, and then that gradually dies back down. As the number of infectives goes up, I can see that the number of susceptibles goes down and drops down, and the number of removeds, as they start recovering from the disease, just a little later, they start going up until everyone is eventually removed from the population. So that's how we go about doing the analysis with the default values. So we have 5 values we have to put in: lambda, beta, delta, 6 values, so we have lambda, delta, beta, delta, delta D, rho, and I. Let's start by looking at lambda. So I'm going to change lambda from 5. I'm going to move that up, down, say to 2. Let's say that each infective person only infects 2 people per week instead of 5 per week. So a total in a 2-week infectious period, if we had one, we knew what the infectious period was, of 4 people. So if I do that, you'll see that now I'm not contacting so many people. Now I'm contacting 2 per week instead of 5. So it takes longer for my disease to explode. But you see, after 5 weeks here, my infectives go back up, and I have this characteristic shape. So if I go up to, say, even 10, that's just extraordinary. There I have a very quick outbreak. I still go up to about the same level, and it drops back down slowly from roughly 85% or 90% all the way. It drops back down gradually. Now let's go back and take the default value of 5 for lambda, and let's see the effect of rho. So rho is my recovery rate. Remember that it's the rate of recovery from the disease, and rho equals 0.1 actually corresponds to 1 over rho as a length of time in the infectious category. So I would have 10 weeks of infectiousness, and that might be not realistic. So let's increase rho, which means we will decrease the length of time. Let's increase that to 0.2. That's 2/10, so that's 5 weeks. That's 5 weeks of infectiousness. So if I do that, I'll see that the disease drops back down dramatically. Of course, I'm not staying infective so long, so naturally we're going to recover. If we look at the infectives here, the disease is going to die out much faster. However, let's say if I go even higher, if I go up to 3, so let's say 1/3, that means I have 3 weeks of an infectious period. Now my curve drops down even further. Notice that what's happened here as people get well faster, 3 weeks instead of 10 weeks, I still have a peak. I still have an explosion. And we'll notice that all of these scenarii, if you want, that we've tried out, have resulted in a tall peak there, but this only goes up to about 60%. So notice if the people get well quicker, then there's not so many people that are going to be infected, and it will die out quicker. So now the last thing I want to check is I want to look at the effect of putting more people into, here we've put 1 in a million here, so suppose that we have even more, even if I change that to 0.0001, we'll see what happens there. I'm introducing more people into the population who are infective, and to see what happens there. You see, the more I produce, I have a very quick increase up to, again, over 80%, and that dies down very slowly, much like the original graph we looked at. So there you have it, the kind of things that we do in trying to look at the sensitivity of different kinds of variables. You can play with the contact rate, recovery rate. What kind of things can you actually influence as someone who wants to combat the disease? You can influence lambda, which means if you put people in quarantine, you're trying to reduce the number of contacts that they would have during the period that they're infective. You will also, as you put them in quarantine, effectively try to shorten the period of infectivity artificially by taking them out of the population. So that's why I mostly concentrated on looking a little bit at lambda and rho, tried to play with them and see what's happening. But this is actually what all the measures are that are being taken, that are trying to influence these two parameters to try to get the peak not to go up so high, or the curve to drop down faster than it would normally. So, but one thing is fairly sure, and that's what period we're in now in the world, is that initially there's a very fast outbreak that goes up to a high level, and the fewer interventions that you try, the higher that would most likely go. So thank you very much. I'm going to take all of this, the text here and the programs, and I will put them in a zip file that you can download, and I will put a link that you can click on in order to get that. So there you have it. Now you're qualified to be Director of Homeland Security. So I hope to see you in another video soon. Bye.